welcome. In this lecture, we are going to talk about loop shaping and design aspect of digital voltage mode control in a buck converter. So, here we are going to talk about, we want to revisit the design step of voltage mode control, which we have already discussed. We want to revisit the design step for digital voltage mode control, and finally, we are going to show some MATLAB case study using digital voltage mode control. So, if we recollect our digital voltage mode control with power stage, because here all the simulation case studies will be considered inconsistent with the experimental case study. That means, we will take the experimental prototype inductor, capacitor, input voltage, output voltage, switching frequency and the load resistance, and this we have discussed multiple times, and this is the architecture of digital voltage mode control. Then we also have considered the feedback voltage gain, which is 0.27 that we have discussed, RAM voltage of 2 volt, that RAM, this is the VM RAM voltage, and we have also discussed this Verilog HDL synthesis of this. That means, this we have kept in a FPGA device. That implementation also we have discussed multiple times with live video demonstration. Now, here if we recollect our small signal model of a digital voltage mode control, we have discussed, I think in lecture number, I believe it is in the 5th week lecture, where we have considered one particular thing. We have a feedback gain which is of a practical converter, and this is approximately 0.27 that we have considered, and we have to accordingly scale this reference voltage. So, this is also there, and this controller, because if you multiply this whole thing, then kf will get cancelled, and it will be our original design which we have considered in week 5, where we have not considered any feedback gain, but here to be consistent with the hardware we have considered kf. So, whatever design will come without any feedback, that has to be scaled by this, so that the hardware implementation, that means this quantity inside this will go to the hardware implementation. Okay. So, we have to consider this GC. So, this GC we are talking about, which will go to FPGA, and multiplication of this kf will be in your actual look like a original gain. And here we will consider this delay, and this delay we have considered sampling delay, conversion time, everything, and we have also discussed that if we consider our traditional small signal model continuous time and incorporate this delay, then it will be reasonable to design the digital voltage mode control, though it may not capture the first scale instability, but this is good enough when you design the controller using small signal model up to 1/10 of the switching frequency. And this is the loop transfer function for the block diagram reduction. You can, kf is now placed here, and now we are talking about the loop transfer function. Now, if we consider the loop transfer function, now this kf gain comes into picture, and the practical buck converter we are talking about, and we have discussed in lecture number 30 in our earlier NPTEL course the design method of digital voltage mode control, how the loop transfer, what are the objectives, the loop shaping objective, all these things we have discussed already. Now, we have discussed in lecture 30 also how to design digital voltage PID controller using stable pole 0 cancellation, and we are not going to repeat again, but if you find K1, K2 for stable pole 0 cancellation, and this Ki of the integral gain, continuous time integral gain, will be coming from the crossover frequency, and typically for voltage mode we choose that 2 pi FSW by 10, 2 pi FSW by 10, 2 pi FSW by 10, that is our typical crossover frequency. And we have discussed in lecture number 43 in this course the design of digital voltage mode control using the continuous time frequency response along with an additional delay due to this particular term. And we have discussed by using both stable pole 0 cancellation, we have discussed in lecture number 43 that how to get this Ki value, then from this Ki and K1, K2, tau d, how to get back the actual Kp, Ki, Kd, and these are continuous time integral gain, continuous time derivative gain, continuous time proportional gain. Then how to get back the discrete time proportional integral and derivative gain, and we know that proportional gain will not change whether it is in continuous time or discrete time, but integral gain in discrete time will be simply integral gain in continuous time into the sampling time. In this case, it is same as the switching time period, and the derivative gain in discrete domain will be simply continuous time discrete derivative gain divided by the sampling time, and this we have discussed in lecture number 43. So, we have also discussed another alternative approach. So, this was earlier was stable pole zero cancellation, and which is highly sensitive to resistance and all, and we will see when you go for output impedance shaping, this method may not be the right way, because when you are talking about the closed loop output impedance. In this technique, we have discussed that if we treat the voltage derivative similar to, because the derivative of the output voltage in a buck converter will carry the information of both load current and the inductor and load current, because we know that dV0 dt, C dV0 dt is equal to IL minus I0. So, that means if we take some fraction of capacitor as a derivative gain, then it actually carries a fraction of the capacitor current, which is nothing but inductor and load current. And we want to utilize this concept for design of the digital voltage mode control. And we have discussed in lecture number 43, in order to design, we typically take the continuous time derivative gain maybe 0.2 times capacitor value, tau d, that is the filter time constant of the derivative filter. Then we have also discussed in the process of design, if we set Kd, tau d and Ki to be 1/20th of the switching, typically Ki we take, here we are taking omega c divided by, I would say, we have discussed that omega c then Vm by Vin, something like that. So, this we have discussed, and here we are taking this divided by 1/20th of this switching frequency. So, this we have discussed, and this is what it is coming here, and there is a alpha term. Now, if you design this, then we have to select Kp such that the loop transfer function, the crossover frequency reaches 1/10 of the switching frequency. So, this is the loop transfer function, and this is discussed in lecture number 43. So, and we also know how to map the continuous time gain into discrete time counterpart, their discrete time counterpart. For proportional gain, it is the same. This is also discussed in 43. Now, we are showing a simulation case study. So, first we are considering input voltage 3.3 volt, output 1 volt, and we are making a load transient from where load resistance is changing from 13.5 to 0.32 ohm. That means a load step size of around 3 ampere, and we got for pole zero cancellation the design Kp, Ki, Kd in the discrete time. These are all discrete time, I would say discrete time gain. These are all discrete time gain, So, we are getting Kp, Ki, Kd in pole zero cancellation like this, and alternative approach like this. And this is the load transient performance, the inductor current, and if you do the same thing for output voltage, you can see the alternative approach can achieve much better load transient response, because we are treating it like a in current mode control is load feed forward, some information. So, you can get very nice load transient response compared to that in pole zero cancellation. And also this method more insensitive to, because it does not consider any pole zero cancellation, and this is a step down transient, and you can see the step down transient also the alternative approach is much superior. And this is a Bode plot. So, in stable pole zero cancellation, we are trying to get a first order loop transfer function, but this is highly sensitive to load resistance and all, and which practically is not possible. But in the alternative design approach, we are getting more or less that 1/10 of the switching frequency, and we are getting reasonably good phase margin. And we will show in the next lecture that if you talk about the output impedance, so this alternative approach is much superior, and it is more or less insensitive to the load resistance variation. Now, if we show the another case study, if the input voltage is now 5 volt and the reference voltage is 1.8 volt, and we kept the same load resistance of the buck converter. Now, in this case the load step size will be just it will be 1.8 times, that means it will be 5.4 ampere delta I0 size, and this is the load transient response in both the approach, and you can see the alternative approach is much superior than the pole zero cancellation, and these are the design parameter. and we will be using this parameter, particularly this alternative approach for experimental case study. And this is the step down transient response, and it is far superior, whereas the stable pole zero cancellation actually is sort of oscillatory, because exact cancellation is not possible and it cannot damp out properly when particularly the light load condition, when the load resistance is high. And this is again the loop transfer function. In summary, we have discussed, we have revisited design step of voltage mode control, we have also summarized the design step of digital voltage mode control, and we have considered some simulation case study of under digital voltage mode control of a buck converter with the similar parameter, power stage parameter, which will be considered in the experimental case study. That is it for today. Thank you very much.